Okay, we're in chapter 5. We're going to cover 2 sections. Excuse me. So in chapter 5, we're going to talk about exponential growth and exponential decay, which I mentioned in previous chapters already. Then we're going to see one live application with banks, with financial institutes. All right. Okay, so the textbook introduced some new notes. See, if we have function of p, right? Remember previously we talked about exponential function standard form as such as a multiplied by base raised by x, right? So a is the initial value. Initial value means when x equals 0, the function value is 8. Right? So b is base, x is exponent, so we call exponential functions. And typically we talk about one case, b equals to Euler number, right? Euler number. So imagine f of x equals to some number, a scalar, multiplied by e raised by x, right? So remember when we differentiate these functions, we can leave a alone, leave a outside differentiation. We just differentiate e to the x. What's the derivative of e to the x? It is itself. There's something special about exponential functions. So that's what this notation means, right? In the derivative function, we always see the original exponential function. In this case, the original exponential function is its derivative. Like k could be 1. In this case, k is 1. So derivative of an exponential function is a scalar of its original function. What does scalar mean? Let's say x. Right? If I do 2x, 2 is a scalar of x. 2 makes x 2 times as big, right? That's what 2x means. Half of x, it shrinks x half, in half. So that's what we mean by scalar. So derivative, the rate of change of exponential function, it just scales its original function, right? Either it makes it bigger or sharper, or makes smaller or lower. Remember exponential growth? Function looks like this, right? Function like this. So the derivative is just multiplied by such k, right? If this was 0, 1 point, then its derivative will be 0k. Let's see 2. Let's use k equals 2. So then 0, 2. Right? Then the graph will be look like this. Or maybe k equals half. That shrinks it, right? So we get a half. Something like this. So that's something about when we differentiate exponential functions. All right, it's a derivative scales the original function, which either stretch or shrink the original exponential function. So if we have this form, if we have y equals to some number, c is some number, some scale already, e raised by kt, then its derivative is, first, it contains the original function. Where you see c and e to the kt belongs to the original function. Then when we take a derivative, we have to take a derivative of the exponent also by chain rule. So that's k. That's why we say k is here. So when we take derivative of e to the g of x, if the exponent of e is a function, well, let's think about e to the x. Well, x itself is a function, right? But what's the derivative of x? Is 1. That's why when we differentiate e to the x, or the rate of change of e to the x, is e to the x multiplied by 1. Well, multiplied by 1 doesn't change anything to have e to the x. So when g of x is not only 1x, is something else, we would have this not a 1 value. Let's see some examples. Okay, so this example wants us to use this. Okay, so we need to make a mental note of this. A derivative of y is c e to the kt original function multiplied by this k. Or we can think, we can rewrite this one as just a ky, because this is just y, right? This part is just y, so equal to ky. So y prime equals to ky. So still a similar idea, but let's make a mental note of this. So this is our first theorem. The function y equals c, some number, multiplied by e to the kt, satisfies the differential equation y prime equals to ky. Conversely, if y equals f of t satisfies the differential equation y prime equals to ky, then y equals c times e to the kt for some constant c. But given as the initial value, we can always find such c. So let's see this example. So we want to determine all functions of y equals f of t such that y prime equals 0.3y, right? K equals to 0.3. Remember so we need to make a mental note, right? Y equals c e to the kt. In this case, k equals 0.3. So that's why we just substitute k into 0.3. So we got y equals c times, c is some number, multiplied by e raised by 0.3t. So in this case, we're not given any point, any other condition, so we have no way to find the c, so keep it as is. But we know c is just some number. Let's see this example. So let's see y equals p of t denotes the number of fruit flies in the kitchen. T days. Since you first observed them, it's known that this species of flies exhibits exponential growth. This is a keyword. So we know the model is an exponential function. With growth constant k equals 0.3. So right away, we can think of p of t equals to some c e raised by 0.3t, right? That's given by this sentence. Suppose that the initial, or this given initial condition, initial number of fruit flies is 6. So which means c equals to 6. The initial means x value equals to 0. Right? Initially, so x equals 0. So number of fruit flies is 6. So that gives us c as 6. So that's it. Then we can write P of t equals to 6. Right? C is the initial value. E raised by 0.3t. So this textbook even go through some calculations. If you want to go through these calculations, that's fine. You just substitute x into 0, t equals 0, right? Then you find c value. So then after 7 days, so how many flies, kitchen flies will we have? So after 7 days, it's a p of 7. It's a substitute t into 7. So we do the calculation, 0.3 times 7, 2.1. So we can go to our calculator, find E. E will be on one of the buttons. Press E, then raise by 2.1. Then multiply by 6. Okay, you want to do the exponential part of the first. Right? Remember pandas? Right? You do E raised by 6.1, E raised by 2.1 first, then multiply by 6. Because if you do by order, if you press C, you press E, then you press exponent, you press 2.1, sometimes the calculator calculate those two values first, then raise the whole thing by 2.1. But what we want is the exponents is only with E, not with 6. So press E, raise by 2.1 first, then multiply by 6. So that's 48.997. So we have to round it up because, we have to count 1, 2, 3 discrete, how many flies. We won't be able to count 49.7997 flies, right? So we just round it up. Let's see this example. This theorem. The theorem says, okay, the unique solution y equals p of t of the differential equation with the initial condition. Remember, initial condition just means the c, right? P of t equals c times e to the kt. Initial condition means the value of c. Initial condition means the variable t or x equals 0, right? When the exponent is 0, e to any base raised by 0 will be 1. So 1 times c is c. So initial condition just means the scalar c. So the textbook changed the c into p naught because we're getting into financial forms. In financial forms, we use principal. Initial principal, we use p naught to represent. Okay, by the way, this is read as p naught in mathematics, p naught. If you want to read at P0, that's fine. So let's see this one. This one's saying, well, we're given K, so basically it tells us K equals 3, right? Initial value is 2. So let's say differential equations with initial condition. So solution, K equals 3, C or P naught equals to 2. So we can form Y or P of t equals to 2 times E raised by 3t, right? So this is P naught, or previously we call C, and 3 is the K value. So everything comes from this formula, C E to the KT. Well, now in this new section, we call this CP naught. Let's see this question. A colony of fruit flies grows at a rate proportional to its size. Proportional to its size. What this is just telling us this is an exponential model. If we use P, that means P prime of T equals to some number. I don't want to use K, just some number multiplied by original one, by proportional. So because P prime of T, proportion means this equals 8, the in proportional. So the division of two things equals to a number, the in proportional. So at the t equals 0, so initial condition, approximately 20 fruit flies are present. That gives us a C or P naught value. In 5 days, t equals 5. There are 400 fruit flies. So P of 5 equals 400. Determine a function. So we need to determine a function that expresses the size of the colony as a function of time measured in days. So we start with this. Then we just plug in what we know. So P of 5 equals to 400. Well, so this is the left-hand side. The right-hand side is P naught. P naught initial condition, which is 20. 20 times e to the k times 5. We know t now, 5. That equals to 400. So we need to set up this equation because we want to find out k. So basically, we need to find out k, right? Because P of t equals to P naught e to the kt. How many variables we have? Well, P naught we already know, 20. E is constant. T is a variable because there's a function in terms of t. All we have to do is find such k. So how do we find such k? We use the condition given. 5 days of 400 flies. 5 days, 400 flies, right? So this is t, this is f of t. Basically 5, f of 5. So one side we have 400. The other side we just plug into this function. Initial value is 20, then e raised by k times 5 days. Right? So we need to solve this exponential equation. So how to do that? Divided by 200. No, divided by 20. We get a 20, right? 20 times 20 is 400. So we get e raised by 5k. Because k times 5, I can write as 5k equals to 20. Now what we do? Remember, we solve exponential equations by using logs. So we take the natural logs on both sides. Once we do that, this 5k comes down. So I have 5k times 1, ln e equals 1. 5k times 1, still 5k. Then this equals ln 20. So k is equals to ln 20 divided by 5. ln 20 is an irrational number. We could just leave like this. So now we can write the function as P of t equals to initial value is 20, e raised by k. K is ln 20 divided by 5, x. Right, so can write function like this. We do not need to approximate ln 20. So leave as ln 20. Okay, so k equals to ln 20 divided by 5. Okay, the textbook evaluated ln 20 divided by 5 is about 0.6. You could do that too. Okay, 0.6 t. Let's see this one. So again, this is given by the exponential equation function, standard function model. The size of colony doubles in 9 days. Doubles in 9 days. What does it mean? That means if initial value, right? So this is initial value. So in 9 days, after 9 days, That will be 2 P naught, so 9 days. Well, after another 9 days, it will be 4 P naught, so on and so forth, right? So what do we do? So we want to determine the growth constant K. So we want to find K. So we want to form, so what do? We're going to use P naught. So this side we have 2 P naught, right, equals to P naught multiplied by E raised by K times 9. Because each 9 days, right, I'm going to just use 1 9 days. 1 9 days is just doubles the original one. The initial one was P naught. So after 9 days, it's going to be 2 P naught because it doubles, right? The word doubles. So I can divide by P naught on both sides. So I get 2 equals E raised by 9K. And now you know how do we solve exponential equations. We take ln on both sides. So 9K equals ln2, right? Because ln e to the 9K comes up front, ln e equals 1. 9K times 1, just 9K equals ln2. Then we divide by 9. So K equals ln2 divided by 9. Well, I guess for this textbook, everything to be approximate, right? So you punch into ln2 divided by 9 on your calculator, you get something about 0.077. And that's it. We have all the values. So now we can write down our equation. Oh, actually, we don't need to, because all we have to do is find the K value. That's the exact K value, ln2 divided by 9. Let's see this one. The initial size of colony in example 5 was 100. So this given P naught equals to 100. How large will the colony be after 41 days? So P of 41 days equals to P naught multiplied by E raised by K. Remember, I already find K ln2 divided by 5, right? Or divided by 9. ln2 divided by 9x, that's K value. Or you could use 0.77. Then just calculation, right? So this equals 100 multiplied by, we go to calculator, we do E raised by ln2 divided by 9. And then x is 41 days, right? So multiply by 41. Oh, yeah, too low. Multiply by 41 days. So you make sure you do E raised by ln2 divided by 9, then multiply by 41. Then in the end, you multiply by 100. The second question is asking how fast will the colony be growing at the time, the rate of change, right? Rate of change is C. At what time will the colony contain 800 fruit flies? So we need to solve for time t, given the P of t is P of 800. No, the P of t is 800. We want to solve for t. D, how large is a colony when it's growing at the rate of 200 fruit flies per day? Or given the change of rate, the rate of change, given the differential derivative, right? So we want to find the t also. So let's just go follow the textbook. So the textbook uses 0.077 for ln2 divided by 9. When it's 41 days, we just plug in t into 41 days to calculate it. That's about 2,350. For B, we use k equals 0.077. We plug into the derivative formula, right? P prime of t equals 0.077 of the original function. If t equals 41, we just plug in, get about 181. Lastly, if it grows to 800, so we have the function equal to 800. Well, what is the function? It's 100 times e raised by 0.077t. We divide it by 100 on both sides. So we get e raised by 0.077t equals to 8. We take a logarithm on both sides. So we get 0.077t equals ln 8. Then t equals to ln 8 divided by 0.77. So about 27 days. D, when the colony is growing at the rate of 200, the derivative is given, flies per day. So which is P prime of t equals 200. We use the differential equation P prime of t equals 0.077 P of t. And set P prime of t equals 200. So then we just divide by 0.077 on both sides. So the original function is 200 divided by 0.077, which is 2,597. Okay, that's exponential growth. We're going to leave exponential decay for the second part.